In this video, we are going to be looking at electron pair geometry and molecular structure. By the end of this video, you should be able to predict the electron pair geometry and molecular structure of small molecules using Vesper theory. The bond angle is the angle between any two bonds that include a common atom. And the bond length, or bond distance, is the distance between the nuclei of two bonded atoms along a straight line joining the nuclei. Bond distance can be measured in either picometers, 1 picometer is 10 to the negative 12th meters, or in angstroms, and 1 angstrom is 10 to the negative 10 meters. Vesper theory stands for valence shell electron pair repulsion theory. So if we take the first letter of each of those words, we get Vesper. And Vesper theory essentially states that the electrons, which are all negative, are going to repel each other. And they're going to repel each other as much as they can so that the distance between them is maximized. So those electrons want to be as far apart from each other as possible because they have similar charges. Electron pair geometries are only going to have to do with how many regions of electron density there are, not what those regions are. So regions of high electron density could either be a bond, whether single, double, or triple, or a lone pair. If I have two regions of electron density, the way they get farthest apart would be a straight line. So that would be a linear electron pair geometry. If I have three regions, the farthest apart they can get is within one single plane as trigonal planar. And all of those angles would be 120 degrees. 360 divided by 3 would be 120 degrees. When I start looking at things that have 4 or more regions of electron density, then we need to remember that electrons are three-dimensional. Or molecules are three-dimensional. So if I have 4 regions of high electron density, they're not going to form a plus sign with 90-degree angles. They're actually going to form a tetrahedral shape where all of the angles are 109.5 degrees. When we go to draw this to show that it's in 3 dimensions, these wedges, the black lines that get thicker as you go out toward the other atom, show that you have a bond that is coming out of the paper toward you. The dashed line shows that you have a bond going behind the paper, and the straight lines are actually in the plane of the paper. If there are 5 regions of high electron density, then it's going to form what is called a trigonal bipyramidal shape. And you've got this axis here, which are linear, so there's a 90-degree angle here and a 90-degree angle going down to the bottom, combined with this trigonal planar feature, so 120 degrees between each going around on the equatorial direction. If there are 6 regions of high electron density, then it's going to form what's called an octahedral, where all angles are going to be 90 degrees, or 180 if you jump over one of those atoms in the way. So all of those angles are going to be 90 degrees between the electron pairs that are next to each other. Molecular structure is looking not just at where the electrons are. Remember, for the electron pair geometry, we don't care whether it's a bond or a lone pair. When we're looking at the molecular structure, we're looking at the location of atoms. Both methane and ammonia have tetrahedral electron pair geometry. Methane has 4 bonds coming off of the carbon. ammonia has 3 bonds and 1 electron lone pair. So they both have 4 regions of electron density. If there are no lone pairs on the central atom, the molecular structure, looking at the location of the atoms, will be the same as the electron pair geometry. However, if there are lone pairs, then the name is going to be different because we're essentially ignoring, in terms of describing the shape, where that lone pair exists, even though it is part of what's giving it the shape. The ideal bond angles that are discussed in the electron pair geometry are if all of the electrons are repelling each other equally. However, lone pairs have more of a repelling strength than bonding electrons. So if I have lone pair interaction, so repulsion between 2 lone pairs, that's going to repel each other more than a lone pair will repel a bonding pair. And that will repel each other even more than 2 bonding pairs will repel each other. So when I look at ammonia, if we remember, the ideal bonding angle for the tetrahedral is 109.5. But the lone pair on the nitrogen repels these bonding pairs more than the bonding pairs repel each other. So that means the angle between the lone pair and the bonding pair will be a little bit bigger than expected, which makes the angles between the bonding pairs and the hydrogen atoms a little bit smaller, and it's actually only 107 degrees instead of 109.5. Likewise, a lone pair will have a greater repulsion than a triple bond, but when we're looking at bonds, the more electrons involved in the bond, the greater the repulsion is going to be. So, if I look at this molecule here, we've got the carbon double bonded to an oxygen, single bonds to 2 hydrogens. There's 3 regions of electron density, which means we would get the trigonal planar shape. The trigonal planar has ideal bond angles of 120 degrees. However, because this double bond is repelling even more than the single bonds are repelling each other, it forces the angle between the double bond and the single bond to become a little bit bigger than that 120 ideal bond angle, and the angle between the 2 hydrogens to get a little bit smaller, 118 and 121 instead of the ideal 120. So again, the molecular structure is describing the relationship between just the atoms that are present, not any lone pairs. If there are no lone pairs, then the molecular structure will be the same as the electron pair geometry. 2 is linear, 3 is trigonal planar, 4 tetrahedral, 5 trigonal bipyramidal, and 6 octahedral. Now, you can't have 1 lone pair if you've only got 2 regions of electron density, or you have just 2 atoms bonded together, which would be in a straight line because 2 points determine a line. But if we go to more regions of electron density, some of those lone pairs are affecting the shape of the molecule, but do not get counted when we're looking at the shape of the structure itself. So if I have a trigonal planar structure, and one of those is a lone pair, then that lone pair is essentially invisible when I'm looking at the structure, and those 2 atoms that I have left are in a bent shape. And if you remember, in the trigonal planar, the ideal bond angle is 120 degrees. That lone pair is going to repel it more, so the angle between those 2 will be a little bit less than 120 degrees. For a tetrahedral, if one of those is a lone pair, then I have 3 bonds coming off of my center atom, and those 3 bonds are not within the same plane. They're pushed downward by that electron pair. So what I have is called trigonal pyramid or trigonal pyramidal. So it looks like a pyramid because that lone pair is pushing those extra electrons, or those extra bonds, downward. If 2 of them are lone pairs, well then if I ignore those 2, I have another form of bent. However, the bond angle here is less than 109. So the bond angles would be different between these 2 bents, but they are still called bent. With 5, I have trigonal bipyramidal if there are no lone pairs. If there is one lone pair, it's going to be called a sawhorse or a seesaw shape. 2 lone pairs will look like a T, and 3 lone pairs, those lone pairs are always going to be on the equatorial region of the trigonal bipyramid, and so those 2 would be in a straight line. Octahedral, if there is one lone pair, it's called a square pyramid. 2 lone pairs is called square planar. Those 2 lone pairs would be along the axis, so everything else is left in one plane. With 3 lone pairs, it's a T shape, and with 4 lone pairs, it's linear. So let's take a look at this molecule and figure out the electron pair geometry and the molecular structure. For electron pair geometry, I have 1, 2, 3, 4 bonds and 1 lone pair. So 5 pairs, or 5 areas of high density for electrons, which makes it trigonal bipyramidal. And with those 5 regions and 1 lone pair, the molecular structure is the sawhorse or seesaw shape. Now, when we have more complicated molecules, we can't give a shape for the entire thing, but we can look at the shape around individual atoms. So let's look first at the electron pair geometry and molecular structure centered around nitrogen. We have 1, 2, 3, 4 regions of high electron density, which is a tetrahedral electron pair geometry. However, one of those regions is a lone pair, so the molecular structure would be trigonal pyramidal. Around this carbon with the 2 hydrogens off of it, I have 4 regions of high electron density, which is a tetrahedral electron pair geometry. Because there are no lone pairs, the molecular structure is the same. The second carbon, I have 1, 2, 3 regions of high electron density, which is called trigonal planar. No lone pairs, so the molecular structure is also trigonal planar. Around this oxygen, I have 1, 2, 3, 4 regions of high electron density, which is tetrahedral, and 2 of those are lone pairs, so it is called a bent molecular structure. So remember, when you're looking at electron pair geometry, you're counting the regions of high electron density, both bonds and lone pairs. When you're looking at the molecular structure, you're looking at the arrangement of the atoms themselves, not just those electrons. So the lone pairs are ignored when describing the shape.